All right, Internet. This is by far the most difficult challenge we've had to face in Natas. And there's many reasons for that. And with that being said, this might be the shortest and worst video explanation I can give on how to solve it. Because I understand kind of how it was done, but not well enough to actually explain it to someone that has no idea. With that being said, let's get started. So why is it so difficult? Well, first off is there's a lot going on, and I was reassured because actually when searching for answers on this specific challenge, there was a lot less provided, and also the people that did provide the answer actually prefaced it with the fact that it took them a lot longer, such as days and hours, to get through this challenge and just to solve it themselves. And there's a few answers I'm going to show you, and then we'll walk into the attack. So the first solution I want to provide, and really the solution I'm going to walk you through because I think they did a great job at explaining it, and I'm just going to read you basically, I'm not going to read the blog to you, but I'm going to walk you through verbally what they've done and how they achieved it. So this is Ozark again, so we have Ozark, and they've done an amazing job, once again, walking you through their code snippet, and not just walking you through their code snippet. What I actually did for this challenge is I copy and pasted their code, and what I did is I did a side-by-side. So I would just walk through, their code side by side next to my code, or not my code, but their code, and I would run it. So I ran their code, saw the response, read through the solution, copied out or commented out that snippet, and moved to the next snippet because there's a few different snippets here. So there's probably I don't know, 7 or 8 different sections of code snippets they used to actually solve this and iterations they had to run through. So I just basically worked through all of that to understand what they did and why they did it. Another 2 solutions I'll show you obviously are Chris Dale, who did a good job at once again going through the discovery process and walking you through not just the solution itself, but how one would go about it if it was a black box situation, which it is in this case, because if you go to the home page, there is no source code. They can't give you the secret sauce, sadly. So that's a good one, and also John Hammond does a good job at explaining his process, and you can see at the very beginning of the video, the first 20 seconds or so is him talking about how difficult this was. So those are 2 good sources, but those are sources we're not going to use today. We're going to use Ozark as our source to understand and comprehend what's happening here. Okay, so I'm putting this off because I am going to struggle explaining it. So for this challenge, we're going to do, I'll explain the attack and then we'll jump into the app and then we'll jump into the code. So the attack that we're doing here is a few things. So we're going to do an SQL injection. So we'll do an SQL-I injection. And that SQL injection is going to be baked inside of a encrypted format. So we're going to have some sort of encryption that we're going to have to basically figure out. We're going to have to understand how this encryption is working. Once we've figured out how the encryption is working, we're going to have to manipulate that encryption to work in our favor so we can include an SQL injection without that SQL injection being caught by the sanitization factors on the back end that we can't see because we have no source code. So the type of encryption that's happening here, at least the mode that's happening, is called electronic code book. So that's going to be ECB. And I'll explain this and I'll walk you through the Wikipedia. But this is the encryption that's occurring. And with this encryption, there's an issue here because this type of encryption is block cipher encryption, meaning that it encrypts in blocks. So say we have a string of text, and say this string of text is 16 bytes long. What this block encryption is going to do is it's going to encrypt this string, and then it's going to take the next string and encrypt that string separately. So say you have maybe a page of text, and that page of text is, say, 300 bytes long. So we're going to basically separate this 300 bytes into a series of 16 block increments, and every single one of those 16 block increments is going to be encrypted. So we'll have these X's as encryption. And that encryption is going to be laying over this. But like I said, it's going to be broken up into 16 block increments. And as this is broken up, when you look through the encryption that's provided in the back end of this app, you're going to see that there's certain segments of this encryption that are identical. So we're basically going to have to break down what's the padding of this encryption and what is our input. And then once we've figured out what our input is in the center of this encryption, say this is our input I, we're going to basically have to manipulate this in a way with an SQL injection to ensure that whatever we put in here isn't desanitized, so we're not getting we're not having our SQL seen as a string, but actually as a command. And then we're going to have to basically figure out a way to re-encrypt all of this and then shove it into this URL to get our answer. So there's a lot there. I'm going to try to break it down here. But if you struggle, no worries, because I struggled and I'm sure everybody else did. So hopefully you glean some sort of knowledge from this video. So with that being said, let's toy with the app, figure out what it does, and then I'll walk you through the solution. So we have an app, Whack Computer Joke Database. Sorry, we can't. We currently are out of sauce, so no special sauce for us, so we can't look at it. And what we're going to do is we're going to search. So we can search on anything. So if I search on D, it's going to basically pull back from the database jokes that have D within it. So you can see D is in keyboard. We have, let's just do control find D. So we have D here, there. So basically any of the statements that have D inside of it, they're going to pull out. Not all of them, but just we're going to be limited to 3. You'll see that when we pull stuff back. Here's our joke. Keyboard not found. Press F1 to continue. An SQL query goes into a bar, walks up to 2 tables and asks, can I join you? Join. Get it? Join. My daily Unix command list. Unzip, strip, touch, finger. Okay. Yeah. I'm not going to say that one because that's a little too risque. So now let's do something that's a little longer and see if we can reduce it. So that's 3. What? Let's do bun. I think I did last time. No, not bun. Let's do fun. Nothing. So that's basically saying that bun and fun are not inside of any of the jokes in this database. So let's do whack. No, I thought maybe computer. If I could spell computer right. Computer. I can't. It's an O. You dumb. All right, so this is just 3. So we're limited to 3, as you can see. What do computer science students use as birth control? Their personalities. That's sad. Okay, so we can see that it's giving us back jokes, and those jokes are basically searching on the word or the letter that we put in there. So another thing we can do is we can do symbols and see what comes back for symbols. So we can see that we've gotten a symbol there. We've gotten a symbol there. There's no $signs in any jokes. I mean hashtags. Nothing there. So let's do quotes. Okay, so it's an important thing to point out here that when we input a symbol, such as a quote, that quote is actually being interpreted as a string. So that's one thing to kind of put in our back pocket when we're doing this specific test here, is that these different symbols, they can sometimes be seen as a command, but if there's some sort of escaping happening on the back end, then we're not actually going to be able to utilize any of this stuff. And escape in the sense that if we have a single quote or a double quote, there must be some sort of backslash occurring here that's actually turning this into a string and escaping its original functionality as a command. So that's happening in the back end somewhere. So our goal here is basically to, once we've broken down the encryption and figured out everything and deciphered everything, when we put our SQL injection inside of this, we need to make sure that we avoid this issue of being escaped, and we're having our SQL injection considered a command and not a string. And the way that's done is cuckoo for Cocoa Puffs. It blew my mind. So let's actually look at the type of encryption here, and I want to show you what it looks like. So if I put in W, you can see we pulled out W. But in the URL section here, we have a huge string. And this string is base64 encoded, or URL encoded, and base64 encoded. And the reason we know that is because we have the %3D at the back end of this. And to show you what that looks like, we can go to CyberChef here, and we can drop this URL encoded situation here. We can do URL, we want to decode that, and you can see it's been decoded here. And then in addition to that, we're going to base64 decode it as well. So we'll say from base64. And what we're doing is we're going to basically take that from URL encode base64, and then we're going to get this out. And this is gobbledygook, and it's gobbledygook in the sense that it's encrypted. So we know that there's some sort of encryption involved. And once you start to play around with a series of these, so if you basically pull out, a series of these W's, so if I just do WW, and then www, and then just keep taking out all of these URL encodings and then copying and pasting them and looking at them in a list, you'll start to see a semblance of commonalities between all of them. And I don't have anything here to show you what that looks like. And I'm not, I guess I could because I like you. Because I like you, Internet, that's why. I like you and I like pain. So we'll paste that in there and we'll do another one here. So this is, this one is 3 W's. So we'll copy that one, put that in there, and we'll do the same again. So we'll do 2 W's this time instead of 3. Copy that and put that in here because orders. Gosh darn it, markup. Okay, so we've put in, this is 1 W, so 1 W, this is 2 W's, this is 3 W's. And we can see here, if I make this a bit bigger, of these different segments, we can see that there's some commonalities between these. And there's differences, obviously, so you can see that there's a difference here. And we can kind of try to find and track where the similarity is. So we have 2FC, 2BJ, 2DDDD, ROQP, 8DCJ, P. So it looks like P is where it stops. So right about here is where things start to get a little different. And reason being is that if you look at before the P, this whole section here, for every single one of these, all of these are the same. And when looking at that, that's a good sign if you actually know what you're doing, which I didn't, so I had to read about this. But if you knew what you were doing, you would know that this section here must be some sort of padding. This is some sort of string. Oh, damn. I forgot dark backgrounds don't work for this. Internet, I'm sorry. We're gonna fix that for you because I care about your feelings and I care about if you can see this. Anyway, so what I was saying is the P right here, right? We have the P and everything before the P. And we know that there's some sort of padding, right? We'll say pad. And that padding is going to be a string of something. So we'll say it's string 1, for example, right? So what this whole encryption piece here, and the encoded, URL encoded, all that stuff, is going to be string 1. So that is something that we can't touch. That's not something we actually control. So what we do control is after this. So this whole section after this, you can see after all of these keep changing, and that's the W's. That's the W's that we put in here. So the 1W, the 2W, and the 3W. And with that being said, that means that when we input something inside of that string here, this input section correlates directly to after that P. And then the section before us inputting it, so whatever's happening in the background here, that's their padding. That's the static string or the static code or whatever before this. This is going to be in all of them. So we know that there's something's blocked encrypt here. So that's one thing that's kind of important to point out here. So once we've done that, I'm going to kind of jump into the type of cipher we're looking at. So we know that it's a block cipher, and we know that it is it's an ECB cipher. And the reason we know that it is most likely an ECB cipher, if I come to this Wikipedia page, take it to the top so we can see block cipher modes. So we have a block cipher, remember, because we're blocking the string. We're not doing it in stream, so it's not stream cipher or string cipher. And we know that it's potentially the ECB cipher. Reason being is that actually you look at this explanation here, and I can switch back to a better color. Color. Okay. So we know that it potentially could be this because with the ECB cipher mode is when you put in plain text, you get out ciphertext, but the ciphertext is always going to be the same. Meaning that if I put in, dog here, the encryption here could be like XYZ, and if I put in dog here, it's always going to be XYZ, as long as we're using the same exact key for the encryption process. So there's no specific initialization vector. So sometimes there's this thing called an initialization vector, which is basically a randomized number that actually convolutes this. There's I think it's cipher blockchaining. Cipher blockchaining, I think, where basically you take the ciphertext from the previous block and then you incorporate it into the next plain text. So when that comes out, they're all connected this way. So that's another way of actually kind of randomizing and mixing things up. But this is the most simplified blockchaining mode. So if we know that this is the case, then when I reflect back at the point that we made previously, here, we know that this is the same text going in and we're getting the same ciphertext out. So there is no randomization here. So that's kind of the logical leap that we had to make to guess, okay, maybe it is specifically this type of blockchaining situation. And then to get it out, you can see that basically you take your ciphertext, you run it through the same key, and you get out the plain text. That's the same process. So that is kind of the estimation here. Another way to actually depict this, which is really good on Wikipedia to actually show this type of setup, is that if you look here, you have your original data that you're putting in through this ECB blockchain mode or whatever, and you're encrypting it using that mode here. But if the key's the same, like I said, and you run it through the same thing, you're actually going to start to see similarities. You're going to see patterns. So we know that within a picture, there's tons and tons of pixels. There's little pixels here. Oh, these little pixels. Oh, the little pixels. And you can see that this white section here is all the same color grade or whatever. So you know how you like the RGB coloring and stuff behind websites. You know this is all the same white. So you're going to get out the same encryption here. So all this is white, and you're getting all the same coloring, you're getting all the same data encrypted the way that it is. So by using this, and there is no randomization, because if there was randomization here, if we were using some sort of pseudo randomness inside of it with an initial vector or something, then you would see something that made no sense. Like all this doesn't make sense here because there's a randomized factor to it. This is not randomized. So that helps us try to guess what type of blockchaining cipher is being used. So that's the first piece. The other interesting thing, before I jump into the solution, is I wanted to figure out why this is a big deal and how it's been leveraged in the past. And actually, if you go to Stack Exchange, there's a really, really good explanation to the importance of actually not using this ECB mode and how it can be leveraged against many different websites. And they kind of break down the different, basically the reasons of why you shouldn't do this and how an attacker can leverage it. They talk about the graphical simulation from Wikipedia, but also there's actually a good point here talking about a specific attack that occurred against Adobe in 2013. And they talk you through the specifics. And interestingly, this attack was so prevalent and so not widespread, but so prominent that actually XKCD made a comic. And one of the I think it's a popular physics comic kind of setup. And in here, they actually talk through about the attack and the importance of basically not using it, making a joke out of it. Because with the ECB mode and you run it without any randomness, it's basically like a massive crossword puzzle. So if you solve the crossword puzzle, you get the password. So that's one thing I wanted to show you there. This is the article they were talking about. And that's that. So now, with all that being said, we are going to jump into the solution. And hopefully I can explain some bits of what we're going to talk about here. So I'm going to clear my terminal and we're going to start from scratch. So this is the code snippet here and all the solutions here. And actually one thing I'll point out here is you can see that they talk through the different steps of them logically thinking through how to solve this problem. They're not just giving you the solution, but they're really walking you through how to do it, which I thought was really, really kick-ass. So here they're basically stating, we're going to print out some of the source code to see what it looks like. And then once they try to do that, they realize that there is no source code. Oh, damn. And then they walk through another part. They're going to discover some of the functionality of what's happening here. They're going to mess around with some of the injection pieces to try to figure out the size of the blocks. They'll mess with the blocks, do some stuff with some A's, and then I'll walk you through the rest. In the explanation, they're going to walk through some stuff here. What I'm going to do to try to explain this to you is actually do a side-by-side with their code and their explanation and walk you through what's happening here. So first things first, actually, when trying to run their code initially, realize that you can't, unless you're using Python 2 or some sort of way to run it that I couldn't figure out. I'm using Python 3, so I actually had to replace this import with a different import that I found the solution through this Stack Overflow, basically stating down here that if you're using Python 3, it's better to use urllib.parse instead of just urllib. Don't know why, didn't read into that. But by swapping this out, you're all good. You just have to edit some of the code here to make sure that it's correct. And once you've done that, it actually works. So let's walk through some of the code. All right, so I am going to open my terminal and we were gonna swap things out. So first things first is we're gonna print out the source code and I'm gonna actually comment out everything else so we're only seeing what we want to see. Internet, this video is gonna be either mind-blowing or horribly boring. Either way, cheers to that. All right. So I'm going to run the script, and what we're doing here is we're just going to run this first little piece of code. They're just going to print out the text on the screen, so they're going to print out the HTML, and they're going to print out any cookies that are coming out of the HTML. And we'll make this a little bigger so you can see it. And we're going to have to change coloring because going dark mode, y'all, because we're extra hacker boys, hacker girls and boys today. So, first things first, start your session, do all the authentication junk. And then what we're going to do is we're going to set up a response, and we're going to print out the text on the screen, so the HTML, which is what you're seeing here, all that stuff. And then we're going to get our cookies, which you're going to see down here. And there's no cookies in the cookie jar. And when looking at this, you can see that their guess is that there's a database involved, and that is a logical guess because, like I said, we're putting in input, it's searching out some jokes, and then it's presenting that back to us on the browser. So there's obviously some sort of something we're doing here. So you can see that we're submitting a query of name, and that's our input. So we're going to submit that into some sort of database, and that's going to be an SQL database. So we've done that, and we have an idea of what's sitting here and all that good stuff. So now we want to actually discover the functionality of the URL encoding. Because when we look at the URL encoding, we see that it's kind of convoluted. So I'm going to undo that one. And we will undo this one, save, run. Now, what we've done here is a few things. I won't talk you through everything, but I'll talk you through some of the main points. So what they're doing is they're submitting, let me open this up. So they're going to submit in the input field, which is here. They're going to submit what in the input field. They're going to push enter, and they're going to get back these answers. That's the code snippet that's happening here. So they're going to submit what and get their response back. Once they got the response back, they're going to print out the text. They're going to print out the URL so they can actually see the convoluted, encrypted piece I just walked you through. Then they're going to do some pretty parsing to do what we did, basically in code inside of CyberChef. So they're going to, undo the URL encoding. They're going to undo the base 24 encoding, and they're going to print out the encryption text itself. And then they're actually going to print out the hexed version of that text. So it's a little bit more human ingestible. So if we open up, not that, so the hexen piece, and then so if we open up the terminal, you'll see some of the stuff I just talked you through. So here we have the URL encoding, so that's the encrypted piece. Then we have them cutting out the base64 piece of that, so that's the base64 side. And then that's the hex dump. So I told you the hex dump piece of dumping out the hex to see what that looks like. And then this is basically the hex dump just stringified. So that is that coming out. So you can see that what they're going to do here is they're going to do a comparison between all of these. Instead of looking at the encrypted comparison, they're going to compare just the hexed version of it, which is what we've already done. But I'm going to show you how they did it, just so you have an understanding of what's happening here. I think I need to uncomment that as well. And we are going to run that. And this takes a while. I'm not sure why they did it this way. I'm sure they could have actually edited this slightly to make it, less painful. And maybe actually I messed this up. Let me do that, bump that over, save it. Maybe this is me and not them. I'm sure it's probably me because this person is very intelligent. 4x in range. Huh? Maybe not, internet, maybe not. So let's jump into this, and I just want to show you what they're doing here at a high level. What they're doing in this specific code snippet is they're running through a for loop, and in that for loop, they're basically going to input what inside of their URL. So they have the text from the page. They're going to do all the the parsing of the query itself, and they're going to iterate through this. And as they iterate through it, they're going to basically add on to their specific query, which is going to be what? And they're going to iterate through this multiple times to see what kind of feedback they can get. So if I scroll through this, you can see it's very repetitive. So we're getting a lot of the same stuff back. But an important thing to point out is depending on what you put in the input field, you might actually get an incorrect error, amount, PK, padding, block size, etc., etc. And I think you can actually get that to happen in the browser. I don't know if I remember how to do it though. Let's see if I can get a TOS 29. I'll just try to look at some of my historical inputs to see if I can get anything that worked. I did bunny a few times. No. Oh wait, no, this isn't what we did. Sorry, I figured out what we did last time. Internet. Sorry. So you have the URL encoding here, but if you actually just come in here and there you go. I just did it on accident. So if you just come into the URL encoding piece and manipulate the query itself from the URL and push enter, it's going to give you an incorrect error. And this is a sign of the encryption process as well. So you can see it says PKS number 7. I had to Google this to figure out what it was. It's a form of public encryption. And then this actually leads to us trying to realizing that it's the block cipher that we talked through already, the ECB stuff. So that's what they're doing here, is trying to figure out what their error means and how it works with this overall encryption. Next piece here is a piece where I will need to make sure that this is unencoded. And if I run this piece, hopefully it works. Haha, here we go. All right, so now they're trying to figure out the block size. And this goes back to the point that within a block, there's a set series of bytes inside of it. So remember how we talked through the basically the 16 byte piece, where you're encrypting blocks of 16 bytes for a 300 character length page or story or whatever. So we need to figure out how big these blocks are for each of these. And in the end, we find out that it's 16, and I'll show you kind of how that happened. But that's what we're trying to find out. And what they're doing here is they're basically doing a range, and they're going to step through basically adding A's to the input. So in the input, they're going to add, they're going to add 1A and do enter, 2 A's, enter, 3 A's, enter. And they're just going to keep doing this continuously, over and over and over and over. They're going to do that 150 times here, you can see. And as they iterate through this, adding the A, they're going to add that in, they're going to submit it, and they're going to basically parse and get the length. So they're going to take that URL encoded URL piece from there. They're going to parse it, they're going to URL unencode, they're going to parse it, they're going to decode the base64 piece, and they're going to print out the hex. Once they've done all that, they're going to get the length of it, and then they're going to count the iterations of what we've gone through. So the first iteration, second iteration, third iteration. And you can see kind of here, looking at what we've gotten out here, you can see at the very top, we have our first iteration, which is 160 bytes in length. We can see our second iteration's 160 bytes in length, and this is the first A, the second A. So if I write in here, oh no, I forgot internet, that the terminal hates my pen. I don't know why it hates my pen, but I hate that it hates my pen. But I think what I can do is I can trick the terminal. Tricked you. So this first one is going to be 1A. Next one is going to be 2 A's, 3 A's, 4 A's, and you can see that correlates to the index here. And what we're doing is we can see that this is going for about 9 iterations, and then it's going to jump to 160. No, here we go, 12 iterations. Here, 12 iterations. And then we're at 160 bytes, right? For the length of the, for the block size, for the bytes inside of the encryption process. And then we're gonna jump in 13 and we have 192 bytes. So that's increased, right? In byte length. And that's gonna be 13 A's. We're gonna keep going and we're gonna get to 224. And if we see this, if we do some, calculations, because, math is hard sometimes. So we have 32 there from 192 to 160, and then 224 to 192 is going to be 32 as well. So we can see that there's a 32-bit jump between each of these here. So now that we know that the jumps that are happening between these are 32 characters basically in between each of these, we know that it takes 16 A's to get to the next jump. Because if we look at the count between 28 minus whatever that is, let's try that out too. So 28 minus 12. Yeah, 28 minus 12 is 16. And then we can keep doing this over and over, right? So we have 45 minus 29. That's 16. So we can see that there's 16 rows in between each of the jumps of the 32 byte jump that we're jumping, and that's the block of the size. The size of the block the size. I'm so good right now, internet. You must be impressed. And my terminal is just really screwing with me right now. So that's the interesting piece there. So let's try to explain this one bit more. So we have the length of the block is going to be 32 bytes, and we know that it takes 16 A's to jump to the next block to get our next length in our next block. So once we put in 16 A's, it's going to jump to the next. Once we put in 16 A's, it's going to jump to the next, and we're going to keep working through all of these blocks. And to make this look a little prettier and more understandable, they've actually, what did I just do there? They've actually created another for loop basically to make it more interpretable. So if I undo this one, save it, and tell Sublime I don't want to buy their product, and run that, you can see what they're doing is they're breaking it out into block size chunks, and the block size chunks are going to be basically ran through up to 47 here, because you can see that we're going to have 47 in total based off of this loop here, and you can see that's correlating to what we're seeing here. And remember, so this length here, so this string is going to be 32, and then it takes 16 A's to get to the next one here, and the next one here, and here, and here, and here, and here, and here. And to quickly kind of show you what's being done here, actually I probably don't need to, it's just a for loop to prettify what we've already done up here. So we're basically inputting a list of A's, we're printing it out, we're parsing it, and we're going to divide by 32 because we know that's the size of the blocks now. And we're going to divide that by 32, do some funky stuff here, and print it out so it looks pretty for us to kind of interpret it as humans. So once we've done that, the next thing is to basically look at these blocks and see if we can find any similarities. And they've walked through a lot of it in their blog, which I'll probably refer to quite a bit. But let's get in here and I'll show you at least some things that are quite obvious once looking at this. So when you look through these different iterations of the blocks themselves, which are basically the URL encoded, unencoded URL piece, decoded and stringified, all that stuff, you can see that the first two blocks of every single one of these ciphers are identical. There's no difference. They're all the same. And that stays consistent all the way through. So if we go all the way to the bottom here, you're going to see that it's the same every single time, the first two. And that is what I referred to when I was talking about the padding. The padding here is the string. Remember I said it could be like string 1 or whatever it is. That's something that's happening in the back end that we have no input on. But everything afterwards, that's our input. Those are our A's. And those A's are being interpreted to whatever this encrypted version of what that is. So we have that piece and we understand that. And that's nice to know. Let me go to the blog and let's see if there's anything I'm missing on that. So there's one piece here, internet, that I kind of understand, but I don't think I understand fully. But we're going to try to explain it anyways. When looking through here, you can see that it's not just the first two that are the same, but the more we progress through these A's, the more the rows become identical. So starting with the first one, we have the first two that are consistent. But once we get to the 10th, we can see that the first three are consistent. So we keep going here and we can see that these are the same. And the third is not being changed anymore. And if we keep going and get to, I think it's 26 maybe? Yeah, 26, you can see after that, the fourth one never changes. The fourth one's all the same. Once we get to 42, that's the same here. So we keep going. So the fourth is the same, the fifth is the same. The fifth never changes here. We keep going, and it's always the same. So what does that mean? That means that there's some sort of padding, and they mentioned that there's padding here to basically explain why this is the case. And that padding is some sort of offset before our input's incorporated, meaning that the first portion of that string is padded with something that we don't have input on. So our A's are actually starting at the midpoint of this block here instead of at the very beginning. So this padding isn't something we don't really need to know, but it's nice to know that that's kind of how that's structured, and our A's will start here. So as we put more A's in here, you can see they have a really good graph here stating that here we have, I think, 10 A's. We have 10 A's here. And when putting in those 10 A's, there's no extra, anything going to happen here. But the point I want to point out is that there's two X's missing here. Reason being is that that is the padding that's being held for us here. But when we add an A for 11 A's, we're adding an X here, so that the block is expanding until it actually turns itself into a new encrypted block. And that's why we keep adding blocks here, and that's why the blocks keep getting longer, because we're adding more A's. So once we've gotten to the 12th or the 13th A, we're actually going to create a new block, and that new block is then created, and that's in the encryption piece we're going to add into. So with that being said, now we need to figure out if there is any escape characters. And the reason we want to jump to that is that we know that our character is being escaped, but we want to see if there's a way to actually get to bypass this. So the next part of the code, I will jump to here. Let me comment that out and jump down here to this for loop. What they're doing here is they're basically looking through special characters, and they're tacking those special characters onto our A. So we have a series of A's, and then we're going to add our special character onto that A as we increment through the A's. And we're going to base 64 encode everything and all that good jazz. So if I come through here and run it, basically it's going to do a count, and it's going to say, I've tried this character, and this is the length I've gotten for it. I've tried this character, this is the length I've gotten for it. This character, this length, this character, this length. And that's basically the length of the block, the block itself that's being encrypted with the bytes. And the important thing to point out here, and my terminal hates me as usual, is that we can see that these three characters have longer encrypted blocks. And the assumption and the logical leap we can make here, if we know what we're talking about, but I don't, is that there's some sort of escaping happening here at the moment. So these characters here are being escaped, and that's automated. So the escape piece is happening here. So if I have a backtick, which is this tick here, so a single quote, right? That single quote is going to automatically have some sort of escape character, such as a backslash. Same applies for the double quote. Same applies for the backslash. So we'll have two backslashes to basically escape this one here. And as we see this, we know that there's some escaping happening. So if we know these characters are escaped, we know that we need to figure out a way to avoid this escape character automatically taking over the piece that we want to use for our command. And that's one interesting piece that's needed to know, and we know that now. Now the next piece is basically saying, okay, if that's the case, then what I want to do is some convoluted stuff, and I'm really going to try to explain hard, and I hope that it works. And thank God they have this table, because this table is super useful for me, internet. So we can see that it's being escaped. So this is the escaped section. This is the clean section. So what we want to do is we basically want to take a series of A's with the escape included. We want to take a series of A's without the escape included. Then we want to basically maliciously manufacture and incorporate these two encrypted strings together to basically make sure that the command that we input isn't escaped because of the positioning of the point that I've put there. And that's a horrible explanation. I'm so sorry. So we have our escaped section, our clean section, and then we have our malicious section. So what we're doing here is we have our backtick. So the backtick is what we input. So let's zoom in here. Oh my gosh. So the backtick is what we input. And once we input that backtick, it's automatically going to have this backslash input. So this backslash has automatically been added, and that's why we had that 192 length. That's why the 192 is so long, is because this was included in that lengthened the string, which basically included this new block, because we had 160 here, and if we just put in something that had no automatic escaping, it would have stayed at 160. But since we put in something that had the escaping, that escaping actually knocked our new character, which is our tick here, to the next block, which is going to be that 192 length, right? So the whole thing is 192 here instead of 160 here. And now we know that that's being escaped. So if we input a string of A's, we're going to have just our string of A's, and that's going to give us 160, not 192. So we need to figure out a way to make sure that we can basically copy and paste this specific block into this clean section. So we have the backtick without the backslash. So when the backtip is executed, we're actually doing a command, and there is no escape here because we've copied and pasted the subset of that encrypted piece into the clean piece. so that the clean piece and encrypted piece, like the bad piece, are all together and it's malicious. Again, horrible explanation, but you know, doing my best here, internet, doing my best. So once we've gone through that process, I actually played around with the code here and I added in some more print statements and stuff to try to make it make sense, you know, but don't really know if I did. But we're going to try anyways. So we have that set up there. And I want to print this one too. And that. So I think if I run this, it will not break. Ha! Look at me. It's like I know what I'm doing, but I don't. All right, so we have a few code blocks. So this code block here is going to be our malicious code block. So that's going to be the code block that included the tick, and that is also going to include a SQL query that's going to basically ask for the database to dump everything. And it's going to be something along the lines of, I think it was like union dump something, something, something. It's an SQL query where you basically can dump out all the passwords. So it's like, hey, SQL, give me all your passwords. And this is like a simple piece that you can quickly look up. It's not hard. But you have the backtick and that piece. And that's going to be incorporated into this encrypted block here. Then we have our clean block. And we can see this block is shorter. And this block only has A's. And there is no badness here. But remember that this bad block that has the backtick has the additional escape character. So we have our backslash and our tick, and that's why this is longer, because we've added a block to it in addition to our SQL injection. So what we want to do here now is we want to copy and paste a specific part of this encrypted block, say this section here, and then we want to basically strategically craft it and inject it into this clean version so that when we get to this crafted version down here, we've both combined our malicious piece, our clean piece, into a crafted piece. Then we can take this, inject it into our browser, and then get our answer back. And I hope that was useful, because I spent not a lot of time, but some time basically figuring out all this junk here. So let me undo that, because we don't need it. But what we do need is this. And actually, what I'm going to do is I'm not going to do it in the terminal. I want to actually show you what this looks like in the browser. So I'm only going to print the payload here, and I need to make sure that I didn't print or didn't, you know, comment out too much stuff, because I think we still need this piece here and this, because it's being called here. You can see crafted's being called, and I think do that. Oh, wait, we don't need that one actually, because we have the response here. Take that out. All right. I hope this is enough. Let's try that. Ah, it is good. So here we have our well-crafted and horribly presented encrypted URL encoded, base64 encoded, all that stuff into this line. So that's going to be our specifically special crafted piece. Now what we want to do here is actually place this into our URL here, and it will hopefully give us the answer. And I think there might be one miss here, because I think if I go in here and paste it in, it's going to error out. Okay, internet, I think I got the wrong one, because you can see that this is a lot shorter than this. So I messed something up. I'm not sure what it was, but as long as our forward slashes are okay and we have no backslashes, I think this one should work. So if we come back in here, we search here, and we delete this one, and put our well-crafted one, and boom, we got the answer. Internet. That was the hardest one, and to prove it, whoever this person is, because they're way smarter than I am, here's a little closure for you. This took me 4 to 5 times longer than other challenges. I can safely admit and claim that this was the hardest challenge in the whole series, by far. So hopefully, the next challenges aren't this hard. Either way, that's your answer. That's how we do it. And I will see you on the next challenge.